Get started. Welcome to How to Better Manage Your Fog-Related Wastes. My name is Ken Grimm. I'll be the moderator today. I am also one of the trainers that does some of the workshops that we have provided, and this is another in our series for PPRC and the Western States Alliance on another in our series of webinars to provide a service to the fog community. So this, the webinars as well as the trainings we've been doing have been provided through funding from the USDA's Rural Development Office. It's a technical assistance grant that helps us not only provide information over the web, but also to get out and provide some boots on the ground workshops, particularly to small rural communities that could use some assistance in managing, developing, enhancing, and promoting their fog programs. See. Oh, there we go. Okay. So the purpose of today's workshop is to discuss how to improve your fog abatement program as regards evaluating grease interceptors. You know, what types are out there, what are the differences, how to select the correct size and cleaning frequency, and just how are interceptors tested? How do we know that they work like they're intended to work? So before we begin, we are recording this webinar. A copy of it will be available next week on PPRC's YouTube page. You can see the URL there on the screen. It will also be linked to in the westernstatesalliance.org website, as well as PPRC's website. So if you have people that couldn't attend that you know of, or if you just like to review some of the material, you'll be able to do that next week. The conference line is muted so that we don't have any background interference. When we get to the end and discuss the questions, I will go through all of them that have been submitted through the window pane. That's our recommended way of asking questions. So if you have something, go ahead and put it in the window pane. And frequently what happens is some of the questions can be answered later on in the presentation, but the ones that are not, we will go through. And at the end of that, I will unmute everybody. And if people want to ask questions directly at that time, they'll be able to do that. At the conclusion of the webinar, you'll get a little pop-up with a short survey. It would be very much appreciated if as many of you as possible could fill it out. It provides the USDA valuable information on what the grant results are and how they're doing, and it gives us a good idea of whether we really fill the need in the community and how we can get better. So with that being said, I am going to pass this along to our two speakers today, Ken Loucks and Clayton Brown. You can see up on the screen that both of these gentlemen have had extensive experience working with fog and fog-related and other pre-treatment issues, and are experts in their field, even though they may say they're not. They most certainly are. So, and with that, let me hand this over to Ken, and he'll start the webinar.
Are we live, Ken?
Yeah, I think I handed it over.
Can you see our screen?
No, let me try this. Nope, that's not what I want. There we go. That should do it.
All right, let me know if you see our correct slide there.
You are up, sir.
So I'm Ken Loucks, and sitting with me here is Clayton Brown. Clayton, I'll let you go ahead and do a brief introduction here.
Clayton Brown, formerly with Clean Water Services, now the Western States Alliance Program Manager for PPRC. As you saw in the slide before, even though the math wasn't right, I have about 33 years in water and wastewater, and the last 15 years I've been working not only as an industrial pretreatment program manager, but also as a fog program manager for Washington County, Oregon. And a lot of the information, a lot of this information is going to be on how to review plans and sizing for interceptors. I also give a one-day workshop on development and implementation of a fat oil and grease abatement program. A perfect person for that because I learned some lessons the hard way, and so I try and keep folks out of some of the quicksand that I got into myself. Ken, your turn.
So I'm Ken Loucks. I am affectionately known as the Interceptor Whisperer, and I have my own consulting firm in which basically I do FOG program development. We do FOG program amendments, so there are a lot of programs that need tweaking, and we help with that. And then I do education on grease interceptors, and I've got a one-day course on grease interceptors that we do live, and then I've got an online course, and we'll talk about that towards the end. So I think this was already talked about by Ken, the other Ken. And then this is who we are again. I don't know why we have all this stuff about us, but so Clayton and I basically put together a joint presentation. So I'll present part of this, and when there's something Clayton needs to interject, and there's usually something that he needs to interject on, then we have him do that. So because the content of this is steered towards really an education in grease interceptors themselves, what we thought we'd do is we'd take you back, we'd give you a brief history of sort of what happened, where did grease interceptors come from, and how did we get where we are today. We'll give you some of that background today that helps us to understand and lays a little bit of a better foundation for you in terms of managing these devices to know about how we got where we are. And so I always begin with World War II, because while the United States did not want to enter the war, in fact, it was our goal to instead become the arsenal of democracy across the world to support our partners, especially Britain. And so we were going to bring all of the industry of the United States to bear on that. And when that led to it led to a realization that we don't have adequate we didn't have anything adequate that related to how we would select uniformly grease interceptors. There were a variety available, but there wasn't any uniform way that they were rated. Each manufacturer made their own devices and so forth. After Japan attacks the United States in World War, that really forced the United States to enter. We were interdicted on the Pacific Islands. We were interdicted from Southeastern Asia, and about a third of our fats were imported from there, fats and oils. And so, we render a fat and an oil, and we get a glycerol, and we use that, and we make glycerin, and we use glycerin all kinds of things. So the military promotes glycerin as the method that we're going to use to win this war. So the way that because we had lost so much on imports, we went through a process basically in which we started with salvaging. We started with rationing. Some will remember some of the rationing efforts of early World War II. A lot of that going all the way towards the end of the 1940s and early 1950s. And so there were a number of things that were rationed, but rationing wasn't going to save our problem. We needed glycerin because we needed to support basically the military used that to say we needed it to support explosives. But the reality was we use glycerin in everything. I could show you a slide that I normally do, but we use it in everything. And so it wasn't just the military that needed it, industry needed it as well. And so there was such a massive demand. And so we then entered into a salvage program. And so in that salvage program, the military decided to take leadership within salvaging fats, oils, and grease, because there's Army cantonments all over the place, Army camp kitchens serving 3 meals a day to the military. And so when it comes to that, now you've got an Army camp kitchen, and it's got fixtures, and they're going to be discharging wastewater like any other kitchen. And so what are you going to treat that with? And we've got these metal grease interceptors. At the time, their cast iron was more typical. But as I said earlier, all of them were rated by manufacturers themselves. So it was difficult to look at the pantheon of available interceptors and know how could you compare one to another. And so the military, wanting everything to be standardized, went to the Iowa Institute of Hydraulic Research and said, hey, why don't you develop for us a uniform rating system? And so the Institute took that project on, invited a number of stakeholders into the process that included not only employees, staff, chemists, and scientists from the Institute, but also the Army Corps of Engineers, the Attorney General, or the Surgeon General, and also members of the Plumbing and Drainage Manufacturers Association. And those were the manufacturers that made drainage products, including interceptors. And so we start to test. Now we're gonna develop a test protocol. From the very beginning, we need to know how grease interceptors are gonna work, how efficient are they gonna work. And I'm trying to summarize for you just the big rocks, the biggest of all of the rocks of this history. Just there's a lot of detail that I normally like to go through that we just don't have time for. So just think of it this way. The Institute decided that they would go ahead and participate. They had a collaborative group that would be a part of this. That group looked at the devices, the job they had. That device was supposed to take the wastewater from a sink, and it was supposed to separate the fats and the oils from that wastewater. The question is how efficient are they? How do they work? Let's make sure that they are efficient. And so the testing methodology would be used to create a uniform rating for them. And so here you're looking at the original drawing of the original test apparatus, which used a supply tank. The effluent from that tank would flow through a valve that was set, a control valve that they would set at and would calibrate at a certain flow rate. And then once they knew that, then they could iterate. In other words, they could test incrementally test over and over and over again just by keeping the tank full up on top, running the test for a set duration, and then using a quick on and off valve. A mixing funnel sits below the feed from that tank, and somebody would stand there with a clock, a stopwatch, and would time themselves pouring in a set amount of liquefied lard over a uniform period of time. So 2 minutes was the test period. And then whatever would enter the interceptor, that's, you hope everything stays in the interceptor, but whatever escapes the interceptor and lands in a catch basin, that needs to be dewatered and weighed. We used lard at the beginning. We use lard today for a very good reason. If you understood how the properties of oils work and fats such as lard, you understand that their specific gravities are virtually identical. They're very close, within 1% of each other. But lard has a very nice advantage. It's solid at room temperature. And so you can allow that to cool, you can dewater it, you can weigh it. You start with something that's a solid, you liquefy it, you pour it in, then you weigh it, you dewater it, you weigh it, you compare that. If I put 10 pounds into that interceptor and I find 1 pound in that catch basin, then I know that interceptor was 90% efficient for that test run. And so the next question then would be, well, what is the minimum performance that we should establish for grease interceptors? And it was decided, for no reason other than the collaboration process, that the average efficiency of the device should be 90%, and that it should have a capacity of 2 pounds of grease for each 1 gallon per minute of flow rate. Those were decisions that were made. They aren't necessarily technical decisions, they're just decisions. And so every interceptor that would be submitted to a test on that would have to meet that minimum criteria for performance. And so now, as we talk about the history and evolution, this is every interceptor that would be sold on an Army installation from that time forward had to have a certificate from the Institute. But the Institute didn't govern commercial interceptors. Instead, the Plumbing and Drainage Manufacturers Association took this testing, all of the data, basically everything that they had learned, the schematics of the test apparatus, and they went to a different agency, a commercial laboratory, and established the first testing and rating protocol for commercial grease interceptors. That we know that standard today as the Plumbing and Drainage Institute's PDI G101, and that was published in 1949. They began to promulgate that fairly rapidly into the plumbing codes. And so while the standard itself wasn't in the code, the performance criteria and the testing, they were. And then one other thing was included in the codes, and that is the sizing methodology that was developed associated with the performance. The sizing methodology established 4 flow rates: 20 gallons per minute, 25 gallons per minute, 35 gallons per minute, and 50 gallons per minute. It assigned those flow rates to fixtures. And so a table was developed that said 1 fixture, 20 gallons a minute, 2 fixtures, 25, 3 fixtures, 35, and 4 fixtures, a maximum of 4 fixtures for 50 gallons a minute. And no interceptor that had a flow rate of greater than 55 gallons a minute would be approved. That from 1949 until the 1970s, actually until the 1980s, that was the Interceptor that was recognized and utilized in the industry. That was those were the legacy style of what today is commonly thought of as a grease trap. That's what we were living with. And so the difference between the military's application of that and the commercial application of that is that the military didn't care about capacity. And so having just 2 pounds of grease for each 1 gallon a minute didn't matter. I have a private, and he's going to be told when to pump out, or he's going to be told when to muck out that grease interceptor. And if it had to happen multiple times a week, fine. If it happened to happen multiple times a day, that was fine. So capacity was never a problem for the military. It's just that in the commercial application of that, where we don't have that same military command structure, now we have a problem, and that is, how do we actually ensure that these things get cleaned out regularly and properly and so forth? And so obviously over time, without the that military command structure, that process waned, and we end up with an industry that really believes these devices are inefficient, they don't work, they're never maintained correctly, they're too small, and they just get a bad reputation because they also are made from a product called metal that tends to fail under a corrosive atmosphere, and so they fail a lot too. So that's sort of the background to leading into the 1970s, in which in 1969 you have the 13th episode of a fire on the Cuyahoga River. It's not the only fire happening on a river in the United States. It's just the one that really became the spark that made change. And so and I don't mean change at the state level, certainly there were states that were dealing with this, but on a national level, there wasn't a national solution forthcoming until 1970, when President Nixon established the Environmental Protection Agency, and he basically said, I want you to go out there and do an investigation and tell us why we've got rivers catching on fire. And between 1970 and 72, the EPA did that investigation. And in 1972, that led to the amending of the Federal Water Pollution Control Act, and basically renaming it the Clean Water Act, and then updating it. And now it funds the construction. So the Clean Water Act now funds the construction of sewage treatment plants under the construction grants program, which meant we were going to start seeing a lot more wastewater, publicly owned treatment works being built out, which meant the associated collection systems that go with those. And as a collection system gets developed, we don't allow a residence or a commercial business that's on a trunk line on a lateral. We don't allow them to not tie in. We make everybody tie in. And so we go from on-site pretreatment, which is the predominant way that wastewater was handled both residentially and commercially. Now we go to collection system treatment, and everybody having to tie in. And so in terms of the history and the evolution, how did things change over time? This became a really big deal, because if you're a manufacturer of a residential septic tank, and let's just take Los Angeles, if you're down there and you've had this big market, and all of a sudden they're building out a fairly large system, and collection system piping's going in all over the place, your revenue stream from building out new residential septic tanks doesn't look real good moving forward. And certainly over the next decade, it started to look pretty bleak. And by the time we get to the late 1990s, there was a manufacturer in Los Angeles who said, you know what, let's take this tank that we've been building and selling as a residential septic tank, and let's find a way to repurpose that. And so they did. So this prefabricator, basically, who was making this tank, decided one day that we wanted to start selling this tank as something different than that. We want to start selling it as a commercial grease interceptor, because after all, whether you're talking about a residence that has solids that are heavier than water, or what oftentimes in a septic tank is simply called a scum layer, it's basically the fats, oils, and grease, the waste fats, oils, and grease from a residence or a business at that time. So we know that the gravity differential separation was known at the time. So this manufacturer simply takes what it knows about grease interceptors and or residential septic tanks, and starts promulgating them now as commercial grease interceptors. Now, gravity differential separation is a really fundamental doctrine of grease interceptors that anybody who's going to manage these devices needs to know about. It simply describes that there's a difference in the weight. Let's use weight for this analogy. There's a difference in the weight of fog and water. And so fats, oils, and grease have a specific gravity or a density that's less than 1, and anything less than 1 will float in water, and anything greater than 1 will sink in water. And the question is, what are the factors that affect gravity differential separation, since all grease interceptors are going to be separating fats, oils, and grease from wastewater? So there's one purpose for these devices, and they all are going to have to deal with this difference in specific gravity. The question is, what are the factors that affect gravity differential separation? There are a number of them, and I don't have time to go through all of that, but I will tell you this. For the sake of brevity, to keep within our time constraints here, you simply need to understand this about gravity differential separation. All of the factors that affect gravity differential separation and how efficient a grease interceptor is depends solely on its ability to mitigate the influent velocity and to create the correct flow environment. So I try to illustrate that by showing you this diagram where we are spreading out or distributing the flow, whatever that influent is and however it enters this device and whatever the shape and configuration of this device is. You must distribute that flow throughout the cross-sectional area, meaning maximizing the footprint across the width and height of the device. And in doing so, you mitigate velocity, and speed is a killer for performance. So we want to try to mitigate the speed by creating a good flow environment. The correct flow environment is a laminar flow environment. So one of the things that we realized as we started seeing over the years the gravity grease interceptor being promulgated, which is a residential septic tank being promulgated as a commercial grease interceptor, were efficiency problems. If you go back to the early 1970s, this prefabricator I talked to you about or mentioned earlier was MC Nottingham, who made residential septic tanks. And ultimately what they ended up doing was converting those septic tanks into commercial interceptors. And then they created a sizing methodology, which they promulgated through the EPA. And then they sold that basically to the Uniform Plumbing Code, the International Association of Plumbing and Mechanical Officials. It gets converted into this thing called Appendix H. Both of those sizing methodologies resulted in very, very large interceptors. 5,000 gallons would be on the small side for many installations. And so we moved from that to, in the early 2000s, to a situation where we no longer use that size of tank anymore. That methodology gets debunked by a task force that Abatement put in place, and they substituted a new sizing methodology that used drainage fixture units and a 30-minute retention time. And in the wake of that, we began to see interceptors that no longer created massive amounts of hydrogen sulfide gas. Instead, they're just super inefficient. And so hard to understand the ditches we keep diving from one to the other, trying to find the right device to solve the problem of, can we just have something that will actually separate grease efficiently, please? And maybe store it for a reasonable period of time. And we thought we were getting that with these devices, but we just haven't quite landed in the middle of the road. And that's because if you look at this drawing, there's nothing to mitigate the flow. And that's one of the reasons that we see the problems with gravity interceptors. The higher the flow rate, the worse the problem is. I don't have time to describe all that for you. If you want to learn about that, take one of my classes and I'll give you all the details, and you'll learn in very great detail why we should expect to see problems with these devices the way that we do.
Water Environment Research Foundation did a long-term study on these too, and there's a lot of data that they put together to show the short circuiting through these large gravity grease interceptors. In fact, I think this picture is one of the pictures that Ken borrowed from one of their publications.
Yeah, I have one that I use of theirs that has a that tries to model what they were seeing in short circuiting. So in terms of, again, we're talking about the history and the evolution a little bit here, and hearing about the mid to late early 2000s, so 2006 to 2008, we start to see a change in the industry, an introduction. There technically isn't such a thing as a high capacity hydromechanical by definition. That's a Ken definition. I'm okay with it. I convinced Clayton to be okay with it because it did distinguish between a legacy style, everything that was made to meet the minimum performance, and that was driven by competition on price, thanks to the military and then the early use of it by PDI, Today we have this, I try to distinguish between the legacy style, everything meeting the minimum performance, to these newer ones today that I do advocate for, I'm a believer in. I don't work for these manufacturers, but I support what they're doing because I believe in it. We have devices now that are much more efficient and that hold as a ratio of grease to overall liquid capacity, very much higher capacities than the old styles were able to do. One of the things that Clayton and I felt strongly that you would benefit from would be a review of the product standards for and how grease interceptors are tested, so that we could sort of illustrate why we advocate when we do fog programs together, or when we do training classes together, when we answering questions with anybody out there, really, why we talk about high capacity hydromechanical as being the direction we want to see the industry go. We want to show you the testing and what that looks like, and how these product standards affect our opinion on that. And so there are these standards that are out there. I'm not going to go through all of these in great depth because of time, but we'll talk briefly about PDIG 101, ASME A112.14.3, and then IAPMO ANSI Z1001, as these are the three most prevalent standards that we deal with every single day. And I'll begin with IAPMO ANSI Z1001 because most people simply are not aware that that's a residential septic tank. But if you go to IAPMO ANSI Z1000, you'll see a canny resemblance to what is called a septic tank under Z1000 to what is called a commercial grease interceptor under Z1001. And in fact, there are a number of issues in Z1001 in which a specifier is pointed back to Z1000 for his answers. So there's no doubt in terms of the history and the evolution, everyone who knows anything about this stuff understands what I'm talking about and understands or recognizes that this is the history. Most people just haven't been told about it. So what you need to know beyond that is there's no testing for a residential septic tank because they are assumed to work. And so the only testing of them is to make sure that they don't leak. And so you have a leakage test, and then you've got loading tests. So if it's going to be buried and you're going to park a car on it, they want to make sure that the car doesn't crash the lid or the top of the box. So that's it. There's no performance test for this. And like this, a device that's assumed to work, only residential septic tanks are sized off of 24, 48-hour residence times. We have this box that's assumed to work off of a 30-minute residence time as a commercial grease interceptor. We just now know that that's just not the case. So your takeaway on Z1001 is it's a concrete or thermoplastic or fiberglass tank that's not rated for performance. So we really don't know how efficient they are. And believe me, when we start talking about, not in this webinar, but if we were to talk about maintenance and inspection considerations, it becomes a very frustrating issue for us to deal with in the field. Let's talk about this then standard for hydromechanical grease interceptors. So if we talk about PDIG 101 and ASME A112.14.3 type A, and you'll see that they're the same. Both type A of the ASME standard and PDIG 101 require an external vented flow control that you see down here. Now, this manufacturer, I believe this is an Endura original style, and they use a separate flow control with a vent control fitting between them. A classic legacy style PDI interceptor will have an external vented flow control that has an orifice plate in it, and then of course it has a vent pipe on that. And positive pressure is on the upstream side of that orifice. We have a smaller orifice to control whatever the flow rate is going into the device. And so positive pressure on the upstream side creates negative pressure. As the speed increases through the orifice, that creates negative pressure that's satisfied by air from the air intake. I am not critical of this device. I believe that manufacturers that test with this device should be required to have that device installed. And so if you are in the field and you're doing inspections and you see a PDI label, the first thing you should be doing is ensuring that that device is installed so that the interceptor is working correctly. One of the most common things that we find in the field is that that's been removed conveniently. It does tend to slow the flow rate down, which irritates a lot of restaurants. So then if we talk about testing, though, you'll see this is the test apparatus, a drawing of the test apparatus today. So you might recall what it looked like before, and it was a test. We had a tank up top that held. Now instead we use test sinks, and we fill those up with tankless water heaters, and we set those temperatures at 160 degrees. And then we take our lard, we put it into we put it into a container, we heat that on a hot plate, we get that into a range of 150 to 160 degrees. We alternate between test sinks, between different test increments. So you see here, I illustrate that with lard in one side. The next test would put it in the other side. You run those sinks together, though. We don't drain one and then the other. You drain them simultaneously, which creates an emulsion. And then that emulsion passes through the flow control device is always right here on this test for PDIG 101 or type A. Under ASME. So it's always going to be right here. So it flows through that and then down into the interceptor. And just like with the original, whatever lard escapes into this tank gets skimmed off, dewatered, and weighed, and then we can determine an efficiency for that increment. So then the question is now, what's happened with efficiencies since the beginning? And here we have a transition in 2012. Prior to 2012, PDI only permitted a maximum grease capacity. There was no distinction. They had one way of rating an interceptor, and it basically said you have to test it to its breakdown point. What is the breakdown point? Well, it's established at the increment. I'm going to explain this. I'll show you in a test report itself. But it's established at the increment that precedes. So there will be two successive increments, and then the one before these two successive that meet this criteria. So the two successive criterias are that either they have an average efficiency that's less than 90%, or they have an incremental efficiency that's less than 80%. What that looks like on a test report, you can see right here. So I believe this is an Endura XL75, 75 gallons a minute here. The way you read a test report is fairly straightforward. Each of the increments are identified here on the far left. The incremental results are the center column, and then the accumulated or average results are on the far right column. And so PDI today distinguishes between a rated capacity and maximum capacity. So a rated capacity allows a manufacturer to stop the test at the 13th increment, regardless of performance, except that it has to meet the minimum performance criteria to be certified. So if in this device, if I put in at 75 gallons a minute, it must retain a minimum of 150 pounds. So if we look down here and we see 191, then we know that it exceeds the minimum. And then remember, the criteria was that it had to have a greater efficiency than 90%. So we see that here. It's over 98. They could stop the run today and be certified at a rated capacity, and you wouldn't know what its actual capacity was. And some manufacturers have taken that and have been a little bit unfair. I'm trying to be kind, but have not reported accurately their actual capacities. And they'll say they'll test to a number like this, and then they'll report it at some much higher number. And you won't know unless you see the test report. Let's look at what breakdown means then. Two successive increments. We get down here on this same interceptor at increments 46 and 47. Two successive increments below 90. Nope, these are both above 90, 96 and 95. Two successive increments where the incremental efficiency is below 80, and I have a 78 and a 34. Those are both below 80. That means that the one before the two successives is 45, and this will be the line that will be used, or the increment that will be used for certification purposes. And this interceptor would be certified at 649 pounds at an average efficiency of 96%. So this is what the breakdown point looks like. This is what the maximum capacity looks like. And I'm going to let Clayton explain this next slide, because it helps you to understand what you just saw.
This is actually a graph of the data table that Ken had on the last slide, where you can see at the far right where it says 95.1%, and then how the line dives down into the right-hand corner. The plumbing contractors and the public works guys that do fog inspections call that catastrophic pass-through or catastrophic breakdown. Typically what occurs in the field is every pound of grease that comes into the interceptor, a pound gets pushed out the other end, and it goes into the collection system. What we found is that municipalities that give a food service establishment 30 days to get their Interceptor serviced after it's already hit this capacity maximum, that municipality is basically letting the restaurant discharge grease into the public sewer for 30 days. Whatever grease comes in goes out. It also, I'm not going to fuss too much on in this talk today, but the 25% rule, a lot of municipalities have what they call a 25% rule, which they've incorporated into their sewer use ordinance, which they have to enforce, by the way. I just found that out a couple weeks ago from EPA. If you have something in your code, you have to enforce it, and it has to be equitably enforced. That means you got to enforce it against everybody that you have that rule, that rule applies to. 25% rule basically says that if a piece of equipment is loaded to 25% of its solid and grease capacity, in other words, there's 75% of volume of water left in the Interceptor, it has to be serviced. So if you look at where 25% is on this graph, it's way over to the right. So if you have a food service establishment that has purchased one of the new max capacity rated Interceptors, but you're forcing them to service it at 25%, then they're wasting a lot of the extra capacity that they purchased. The other issue that was driven home to me, where I worked at Clean Water Services in Washington County, Oregon, we had a grease receiving station at our large Durham wastewater plant. And the guys that ran that really didn't like having pumpers bring in fuel that was 75% water. They really liked a lot more grease in the loads when they came in. So if your municipality is trying to recover energy from this grease, it's better to encourage your food service establishments to put the high capacity units in and then service them somewhere before the breakdown point. So typically where that blue arrow is, or just a little bit to the left of the red lines there. So somewhere between 80 and 90%.
So let's quickly try to cover the way grease interceptors are sized. And I'll just say that the plumbing codes that we rely on, and in fact, a number of different pretreatment programs also use a basic volume sizing or a flow rate based sizing methodology. And the challenge we have with that is that it only considers the flow rate of the device. And yet, when we look at a restaurant, I think if I asked a room of 100 people, do we believe restaurants are producing grease? Everyone, I think virtually everyone would raise their hand. Yes, we do. Well, then why isn't the question how much grease that is? And that's one of the things that we've begun to see the industry shift to. So the proper way to size an interceptor would begin with flow rate, which is all this table is really about. And our point isn't to try to teach you how to size, but rather to just illustrate how sizing is done and what we advocate for, which is what we think is a better way to do this. We actually took a study from this brown grease supply study that was done for Clean Water Services back in 2011, which was basically to validate the feedstock available to them for co-digestion. We were able to work with this study and the facilities that were in it and create a methodology for evaluating how much grease is being produced in pounds per meal per type of restaurant. And this was in 2016-17, is now incorporated in the ASPE, that's the American Society of Plumbing Engineers, their handbook, volume 4 on plumbing components and equipment. This table here is now included in that as an alternative method for evaluating grease interceptor selection, not sizing, but selection. So you'll always size based off of a flow rate, but then you have the options to select something different by using this as an aid to that. And so we originally came up with this low, medium, high, and very high categories. We began to see some pushback in the industry because if you're in pretreatment, you've talked to a restaurant, they'll all tell you that they don't produce any grease. And so we decided to try to demystify the fact that you are not an evil person just because you produce grease. We just need to try to make sure we have adequate abatement efforts in place here for that grease. So we've redone that now, and there are these 30 categories of types of restaurants. And then whether they, you can see here at the top, without fryer, without flatware, without fryer, but with flatware, and then of course with fryer, no flatware, with fryer, with flatware. Those are just categories now. So if you are a burger and fries fast food joint and you have a fryer but you don't have flatware, then of course that's going to put you at 0.035 here. If I have that line correctly on my screen, 0.035 would be the factor per meal. And then we take that factor that I just showed you there, we multiply that times the number of meals or customers per day, and then we just need to determine what our frequency of pump out is. What's acceptable to us? Is it once a week? I don't think so. Most people won't do it. Is it once a month? Well, if they're a bad performer, then we're going to have to back down into something that's more often than once a month. And honestly, if we're not at least once a month, we should probably expect very low compliance. And so if I want compliance to improve, I want to extend pump out frequencies to something that they will find affordable and manageable within a restaurant's operation. So that would determine whatever the capacity is that I need in that interceptor. And since all grease interceptors are rated for a flow rate and a capacity, that makes sizing them by using capacity very rational. So if I give you just a brief example here, Italian restaurant with fryer, with flatware, with fryer, with flatware, a 4-inch drainage pipe, outdoor installation. If I follow the code, it says a 4-inch drainage period, outdoor installation. We can use a 2-minute drainage period. I don't have time to justify that to you, but that would be acceptable. And so we could use that as a minimum flow rate for this example. And then if we look at an Italian restaurant here that has a fryer and flatware, then that's a factor of 0.0455. In this example, we happen to know it's a live example, a real example, serving 469 meals per average per day. We can plug those numbers into this formula, and we see that this Italian restaurant produces 21.3 pounds of grease per day, or 639 pounds of grease per month. And that means I'm looking for a grease interceptor that satisfies this sort of fog production. And so if I look in the 75 GPM category now, because that's the minimum flow rate, I have legacy styles here that have 150 pounds, even this zern here, which would give me once a week. And I am confident they will not do that. So I look here at higher capacities that get close to what they're producing on a monthly basis, and I see 26 days, 31 days, and 30 days. And I think, well, if this kitchen, which I happen to know this restaurant and they were terrible, if they have really, really rotten kitchen BMPs. In other words, if they treat every sink or every opening on the floor as though it's a garbage can, then these numbers aren't going to be realistic. And that turns out to be the case there. So I would want to look to the next category. I'd want to move up to 100 gallons a minute and see what my options were. And you see here in legacy interceptors that's still only 200 pounds. 9 days is not going to be adequate. But as we begin to look here at some of these high capacity alternatives, we see this Endura XL100 at 1,058 pounds giving us 50 days. That's more reasonable. We see Shear's new GB250 at 1,751 now, 82 days. I think that's very rational. Trapzilla's TZ1826, again, 86 days, another very rational choice. And when you start to look at the cost of maintaining these devices on an annual basis, I think I assumed here was $150 or $200 to pump these out. And so you can see it's not very much. And so that would certainly fall within affordability for a restaurant, as opposed to $7,668 a year and so forth. Now you see here that I've listed where the industry is progressing towards, and that is Shear has launched this GB500 and GB1000. And this is a 1,000-gallon tank, and this is a 500-gallon tank. And these are tested and rated for performance. And at 1,000 gallons, I have 6,547 pounds. I have at 500 gallons, 3,049 pounds of capacity. So that gives us more like 143 days and 307 days. I can tell you that I would not be a fan of installing this device for a 307-day pump out frequency. I don't want whatever that effluent is in 307 days. And I don't want the problems. And Clayton can describe it, what he might object to about that. I don't want that.
One of the things that happens in an interceptor is that the material inside of it can go aseptic, or a facultative bacteria and other organisms will start to break down the material in the interceptor, and it generates hydrogen sulfide gas. In fact, we have heard of people that actually died when they opened up interceptor lids without venting them properly because they were overcome with H2S gas. One of the things that Ken mentions, if you look on the right-hand column, you see the maintenance cost. When a restaurant is being constructed, they're looking at the capital cost. What does it cost to build this restaurant? And typically they choose items that meet the minimum code because they're inexpensive, but they don't look typically at what the maintenance cost is going to be for that item. It meets code. It's a small interceptor, because as you noticed through this exercise, if you just meet the 75 gallon per minute plumbing code for flow, you can choose a small unit that's inexpensive to install, but it eats you up on the maintenance side. So this has been a really good exercise for a lot of restaurant owners to go through this, going ahead and running through these calculations so they can see that the maintenance cost versus the capital cost. What's their payback period?
Yeah, this device here would pay them back to install a correct device. This payback period has got to be 2 years, and you're paid for this device, these new devices, as opposed to these, which are terrible. Just to keep us moving, we advocate for all fixtures to be connected for a reason. We believe in the idea that an industrial user, which technically a commercial user is, should be responsible for 100% of their effluent. And we find situations like this where they're running everything through their pre-rent sink, and if that has a food waste disposal unit connected to it, the plumbing code says that should go directly to sanitary, and so we discharge all of our greasy waste direct to sanitary. Happens all the time. We may or may not have a mop sink connected. Well, what about our floor drains and floor sinks? Well, this guy washes the floor and squeegees it all into that. And what about the location of our ice makers or our indirects? Say, here's an ice maker with its condensate drain, and that could be sitting next to a fryer, and in many cases they are, and that could be filled with all kinds of fun stuff coming out of the fryer. And what about food waste disposal units? They are pretty massive offenders, and so if we're not capturing all the fixtures, we're not capturing all the fog. And that's one of the things that I think Clayton can explain with this slide.
In Washington County, we did a series of case studies where we worked with restaurants, and a hospital. There was a commercial facility. The hospital's on the far right of the graph. We worked with these facilities. These were all built under the Oregon's old plumbing code, where they only had one fixture connected to an interceptor. And we tracked the amount of grease that they took out of that interceptor on a routine basis. That's the blue bars on the graph. The restaurants did a retrofit where they connected all fixtures and drains to a high capacity unit. And on average, we capture about 10 times more grease when all fixtures and drains are connected, even restaurants that have employed the best internal kitchen practices that they can. So this is just an illustration to show. This is actually the data that we took to the Oregon Plumbing Board to get the Oregon code change to require all fixtures and drains be connected to an interceptor.
It makes a big difference. And then of course, most of these have a new high capacity device, so it makes them more affordable devices to maintain, as you saw from the previous chart. So we're big fans of high capacity for a reason. We're getting the performance that we want, and we're getting closer in terms of capacity. There are restaurants, you saw that GB 1000 holding 6,500 pounds. You might see that on this hospital, but do I want to see that sitting on something like this Mexican restaurant where it would only need to be serviced twice a year? No, I don't really want to go beyond 90 days. But this does help you to understand how important it is for us to be looking at the new technologies, the new direction this industry is going, and really why we advocate for moving away from non-performance validated devices like gravity interceptors towards third-party performance validated products like high capacity. We offer you some other resources here. This is the fogtraininginstitute.com. Actually, don't enter the www. I learned the hard way. It's just fogtraininginstitute.com. No www. If you Google Fog Training Institute, you'll find it. Right now, so we're Clayton and I, Western States Alliance and I have been working together to collaborate on building out this online teaching platform. And that's really what this is. So we want people to have a place to go, a resource where they can learn about whatever it is that's relevant to their industry. So we're currently the first class I got up and running as quick as I could, which was not quick at all, but I got it up there, which is the Grease Interceptor training course for 2019. Everything you need to know about commercial grease interceptors. So you can take that online. It comes with videos for each of the courses. You have to watch the video. You have to pass a quiz. And when you do all of that, then you get a certificate, and you'll be awarded 0.6 continuing education units in Oregon, Washington, and Idaho. And if you go to that online and find that, you'll also see in the introduction to the course, you'll see the other states that we have approvals from and what those continuing education credits look like. So, and then just email me if you're like, hey, I'm in this state. Somebody just emailed me from Colorado. Hey, once you get Colorado up on your list, please. So I'm working on it. Any comments on that, Clayton?
Yeah, one of the things Ken didn't mention is if your city is a member of Western States Alliance, then you get a discount for the cost of the training. And if you go to the next slide, we're in collaboration with Swift Comply, which is a company out of Ireland. They're here in the United States now, and they make really awesome software to track grease, a grease abatement program. Essentially, it's a 3-module system. We recruit the pumpers in the local area to become involved, so they've created a profile. The restaurants create their profile, and then the cities they carry the data for both the restaurants and the pumpers. On the pumper's profile, he can see any of the restaurants that he has a contract with. The restaurants can see who the pumpers are that are available to do service work for them, and then the city gets as soon as the pumper does service and submits a report to either the restaurant or the city, that data is live. So your manager or your inspector can look at. I don't know if we don't have the other screens. Swift Comply has representatives here in the Portland metro area and also down in San Francisco area that can do live demos for this. Right now in Oregon, City of Gresham and the City of Bend are using Swift Comply, and we have most of the pumpers in the Portland metro area that are able to submit reports on this. Again, there's a discount for Western States Alliance members. We do 2 workshops, Western States Alliance and the Pacific Northwest Source Control Training Association, which have merged now under WSA. We do a pretreatment workshop that typically occurs in September in Vancouver, Washington. We do a fog workshop. It's a 2-day workshop, and this next year it'll be in Hood River, Oregon, the last day of March and the first 2 days of April. And we've also talked Ken into using one of those days to give his full-day workshop on fat oil and grease abatement. So there will be an extra fee for that. But they're awesome workshops. We bring people in from almost all of Region 10, some folks from Region 8 and Region 9. We have folks from Canada that have come down. We've also had people come over from the East Coast. So we kind of cross-pollinate with other pretreatment and fog workshops, the Southeast Fog Alliance, AZ Fog, and the pretreatment workshops like Region 8 pretreatment workshop and the National Association of Clean Water Agencies. So these are some of the resources that are available, and we encourage folks to attend these workshops. They're great for networking, and there's also a lot of good technical information that's going to be presented, especially at this coming year's Fog Forum in Hood River.
Okay, with that, we'll go ahead and turn the meeting back over to Ken for moderating any questions that we have.
Okay, thank you, gentlemen. That was very enlightening, and we appreciate your time. I only have one question at this point in time, and I have a feeling that not everything came through because it simply says require them to get a grease trap. And so what I'm going to do is I'm going to unmute everybody, and if the person that asked that, if there was more to that question, if you could please re-ask that to us, that would be very helpful. So should have everybody available now. Yeah, Jake?
Yes. So I was asking if they're claiming that they're only rinsing vegetables or anything like that in sinks, is there any harmful residues that we could be looking at that could cause some issues to the sewers that would require a grease trap? Hello? Hello?
Yeah, I hear you. I don't know if,
Okay. Sorry. So did you hear the question?
There we go.
yes.
There we go.
So I just,
Okay.
for some reason it muted Ken and Clayton and I just did that. So they should be
Oh,
available.
okay.
If the question regarding a facility that processes vegetables, and that typically that would fall under the pretreatment program. So you may end up with a solid separator. I don't know if there would be grease, but you may have some organic loading. So if you have a pretreatment program that regulates industries based on loading and flow and solids, that may be where you would cover that facility.
Okay.
Regarding any kind of food service establishment in the state of Oregon, whether it's covered under the Health Department or Department of Ag, any place that produces food that's commercially available, either for consumption on-site or off-site, has to have all fixtures and drains in the kitchen and food service area connected to an appropriately sized interceptor. Even in Oregon, even the wine bars have to have an interceptor.
Okay.
There may not be much grease from that facility, but they still have to install an interceptor. Coffee shops, delis, ice cream folks, Subway, Papa Murphy's, all of those facilities have to have a grease interceptor under the state plumbing code in Oregon.
And then if you're talking about a restaurant and you're asking the question whether it relates to a dedicated fixture, there is no such thing as a dedicated fixture. We have a wonderful title for a fixture on a set of plans. We have the intent and purpose of an engineer by specifying it. But then we have the operation of the kitchen, which does what it wants. And if that fixture is convenient for other uses, it will be used for the most convenient use when it's needed. So that's why we advocate for all fixtures to be routed to an interceptor. We don't gamble anymore. It's just not worth it.
Okay. Yeah, I only asked that because we, for our ordinance and the historical value of the city, we just can't have everybody throwing in the grease interceptors. So we have to do the small hydromechanicals under the sinks. And I just wanted to make sure that I was catching everything.
Yeah, I would capture all fixtures if you can. And I'm not a big fan of just using legacy style traps underneath kitchen sinks. I want to see bigger sizes. If you start to walk through some of the exercises about grease production with your facilities, you'll begin to realize, hang on a second, maybe this isn't the best policy. And that usually starts the conversation of maybe we need to start taking a look at our program.
Okay.
Are there any other questions for Ken and Clayton?
Well, there's one thing I want to say. Ken didn't mention this. Ken Grimm didn't mention this at the beginning, but we just completed 26 or 27 one-day workshops across Region 8 and Region 10. And we just received another grant from the U.S. Department of Ag to continue the technical assistance for the next year. So keep looking at the Western States Alliance website on the training calendar, and we'll be bugging Ken Grimm to make sure he gets all of the training events up on the calendar as soon as they're ready. So we're also, Ken Loucks with IW Consulting also does training, but his are typically scheduled and requested by cities. So the contact information there at the end of the slide. Thanks.
Any other questions? Well, then with that, we will wrap up this webinar. Thank you to everyone who attended. Thank you to Ken and Clayton for providing us some really good information on grease interceptors. And like Clayton mentioned, look at the Western States Alliance website for future trainings and webinars. And with that, we'll say thank you again for your participation and goodbye.